Visualizers are the most common way for us to get reactive visuals to sound. Not only do they look cool, but they also give us information about the amplitude of various frequencies in a given sound, something that mere level meters fail to represent. Moreover, certain visualizations like the spectrogram gives us a complete show of the frequencies as a heat map. These spectrograms are some of the most essential tools in audio, whether that be in digital signal processing or even machine learning. And by the end of this video, you'll learn how visualizers and spectrograms work, along with making a spectrogram yourself with just some basic programming knowledge. But to actually convert auditory signals to visual representations of their frequencies, visualizer or spectrogram, like anything when it comes to audio, it's all just bloody math. Now listen, if you know nothing about the discrete Fourier transform, I'd suggest watching my other video on the topic, as I'm not gonna rehash all the stuff I talked about there in this video as well. We will be here for an hour. If you don't want to, from now on I'll refer to all of you all as blue cylinders. I'll still try and explain everything as simply as possible, but it won't be as clear to you all like it is to the red cylinders. Those being people that understand it already, or people that have actually watched my video. But despite all of that, let's look at the discrete Fourier transform once more. The discrete Fourier transform, or DFT, converts our audio from the time domain, which is what it's usually in, to the frequency domain. The transformation from waveform to visualizer, or amplitude over time to frequency over time. Well, not yet really, but I'll explain it in a bit. We input a section of audio into the DFT, and we are outputted a list of complex coefficients, which are essentially all the numbers that would give us the magnitude for each frequency we tested to see if it's in our signal. As all the DFT does is create multiple signals, each with pure tone frequencies. It then compares it to our original signal and say how similar they are, finally giving out different complex numbers, which you could think of as being something like quote-unquote similarity values. These complex outputs can then be used to show the magnitude of the frequencies tested, as well as the phase. You don't have to know about complex numbers, just think of these as numbers that just give us the magnitude, okay? Just chill. But here's where the problem lies. We shove in our entire piece of audio, and we're given a list of values that show us all the frequencies in our piece of audio. But our output gives us the magnitude of the frequencies across our, again, entire piece of audio, giving us a somewhat average of all the frequencies we're testing for. This isn't ideal since the frequency content of recorded audio changes consistently. Whatever frequencies that are present right now are different from the frequencies present 2 seconds ago, and the more I yap, the more they change over and over again. Now at first glance, this might seem like a big issue, and one that might need a multitude of mathematical equations and profuse and rigorous problem solving. But like, what if we just did the DFT and then do it again a little bit later in the audio, and then do it again for a little piece later in the audio, and then do it again for a little bit later in the audio? The short-time Fourier transform is born. It's an equation that allows us to carry out the DFT multiple times on little pieces and stitches it together, giving us the evolution of frequencies over the piece of audio. Kind of like making an animation of the frequencies, where each frame is a little piece of audio we did the DFT on. Wait, aren't these actually called frames? It looks like this. If you're comfortable with the DFT, you can see that it's really not that different. If you're not comfortable with the DFT, then it's okay. I won't go through the entire mathematical equation. Is what I would say if I cared. Just like the normal discrete Fourier transform, we're multiplying each sample of our input signal to each sample of a pure frequency sine and cosine wave, and adding up all of those products to get one of our complex outputs. This operation happens for capital N divided by 2 plus 1 amount of times. Capital N being the number of samples in our input audio. The number of frequencies we look for in our signal is the same as whatever capital N is. So we get capital N amount of frequencies we're able to test and get as outputs. We really only care about capital N divided by 2 plus 1 number of frequencies, but I'll get to that in a bit. But for today, capital N in this case is instead the number of samples in a frame and not the entire piece of audio. If you're really blue and don't even know what a sample is, every existing piece of audio that is brought into the digital realm is digitized by a discrete number of samples, and that's how audio is represented. You can check out any of these videos I've made for more information. But one thing they don't cover is why we only do N divided by 2 plus 1 frequencies instead of just all N frequencies. This is because if we were to plot the magnitudes of all the frequencies we tested, whatever sample rate we have our audio at, the usual ones being 44.1 kHz or 48 kHz, we get a complete mirror of computed frequencies after the highest frequency our audio can contain. The highest frequency that our audio can contain is always half our sample rate. So 22.05 kHz or 24 kHz respectively. Since the output we get on the last half is always the mirror of the frequencies on the first half, we don't have to concern ourselves with the last half. And our audio is never going to have frequencies above that half point anyway, so we really aren't losing any information by just omitting it completely. As a bit of a stickler for correctness, this is also because our audio is a real valued signal, not complex. That goes a little bit more in the mathy realm, but just if you don't know about complex numbers, then you're a blue and that's okay. But just know that if audio was a complex signal, the last half would actually have important information for us. But since it's not, and audio never will be, then we can omit that last half without a care in the world. It also saves us computation time, and I mean, who doesn't like that? Frames are the little pieces of audio we divided our entire piece of audio into. If we had 4 frames, for example, we'd have 4 pieces. But in general, frames are denoted less by their number, but by their size. And capital N, in this case being the size of them for the short-time Fourier transform, or STFT, as opposed to our entire audio, like the DFT. That's the only real difference for our existing variables. As for the new variables, first off, we have M. M is the current index of whatever frame we're on. Capital H is the hop size, and this WN signal here is our windowing function. We can see that our output is now 2 lists. A list of values corresponding to whatever frequency we're testing, with another list, this time being of frames, containing each list of corresponding frequency values, therefore creating a matrix as our output. Don't be scared by the word matrix. You're basically making like a gene thing, like, you know, like this biology gene thing. You're just making that, like, it's just prisoner dilemma, you know, matrix math word. I don't be scared. Each frame index contains a list of values that define the frequency content of that frame. I think this might be better explained with a spectrogram, and lucky for us, this is exactly what this is. Since any image, spectrogram, or whatever you have saved on your computer, is just a matrix of pixels. Each column of pixels or group of pixels is the current frame we're on, and each row shows the magnitude of the frequency at that point in time. We know if frequencies are higher or lower based on how saturated it is. The more color we have, the more a certain frequency is present. Before we can get to this point though, there's still the hop length, and more importantly, the windowing function. Like I said in my granular synth video, a windowing function is something that when applied to a signal, warps the signal to follow its area. It's used in places like statistics and other areas, but in digital signal processing, it's used to combat spectral leakage. Another question I left off with in the DFT video is, what would happen if we're not able to create a frequency through our discrete indexes that match a certain frequency present in our signal, since we can only test a discrete number of frequencies as discrete values? Well, those lost frequencies get spread out all across our outputs for each discrete frequency value, thereby leaking into all of them. I think it's better showcased visually, so here's a DFT output where we can exactly pinpoint a frequency in the list we are testing, and here's a DFT output when we can't. And the only difference is something around 4 Hz. We can make an estimate of how that spread works since it follows the sinc function, since that's what's under the hood of the normal continuous Fourier transform, and how the DFT is just a discrete version of that, but we'll ignore all that for now. You can check out my Patreon if you want to hear more and support the channel, or you can check out this page, links here in the description. It doesn't delve into it deeply, but it's enough for you to understand it. For now, leakage bad gives us muddy output where we can't actually tell what frequencies are present. How do we fix it? Well, it's the windows, isn't it? That's what I was talking about before I went into this big explanation. Every time we input a piece of audio into our DFT, we're low-key always giving it a rectangular window. Even if we're not manually doing it, the nature of the DFT just sees the audio as a rectangular windowed piece of signal. A rectangular window looks like this. It doesn't affect the amplitude of any points of our audio at all, and so whenever we have a non-periodic frequency in our full window and we don't have a frequency index or bin to mark it as, we get leakage. So all we really have to do is try and make it periodic, and we can do that by applying another window. There are a bunch of different ones for different purposes, but one of the most famous and generally used is the Harning window, which has a certain bell-shaped curve that tapers the ends of our audio, which means that we start and end at 0, almost like it's periodic. This doesn't eliminate leakage entirely, but the amount of help it does outweighs what it can't. To show the effects of this window, I've made a whole complete different frequency output where honestly it looks just fine as it is, or at least well enough. But once we add the window, we see that the amount of leakage that occurred was covering an entire different frequency. Now you can see that the peak magnitude has been reduced, mainly because the horn window more or less just sands down our output, which is good for seeing hidden frequencies, but does reduce overall magnitude. Still, dealing with peak magnitude is a lot easier than dealing with something that we didn't even know existed. Going back to the STFT now, this WN is our window function that's applied to each frame to minimize leakage. Again, there are a bunch of different ones, but for the rest of this video, the only value of WN is going to be the horn window, which also has a mathematical equation like this. Don't worry about it, it's usually implemented in whatever library you're using, so you don't have to write it out by hand unless you don't have a library or framework that has it, which was the case when I was part of this team that made a granular synthesizer from scratch. It really isn't the best, but I'd be lying if I said it didn't make me see things I've never seen before. The hop size is a variable stating where the next frame should start. Since we are dealing with little bits of audio, if we were to apply the window to all those little bits, our audio will look like this, where we have continuous little dips in our audio. We don't want that, and so we overlap frames, with the hop size telling us the distance between the start of the first frame and the start of the next frame, thereby dictating the overlap. There are ways to determine what the best hop size for each application should be. However, since we're only visualizing the signal, we don't have to put too much thought into it. When using the STFT for signal processing, the Koala requirement for hop size is important for avoiding artifacts. For usage as a spectrum analyzer for measurement and display, the Koala requirement can often be relaxed, as doing so only means we are not weighting all information equally in our analysis. Even with edges being slightly muted, overall, nothing disastrous happens and the results look just fine. And we're already on page 4 of this script, so we're gonna pick a hop size of half the frame size and call it a day. But speaking of which, we also have to pick the frame size, which should always be a power of 2. The reason being is, although we are using the DFT for each frame, the actual implementation is the FFT, or fast Fourier transform, which is the DFT, but it runs a lot faster as long as it has an input that is a power of 2. And who doesn't like faster computation? There are certain trade-offs to consider when picking the size. The larger the size, the more frequencies for each frame we're able to test for and get an output for. But the more averaged out the frequency analysis would be over time. Higher frequency resolution, lower time resolution. And inversely proportional to that, the lower the frame size, the less frequencies for each frame we can test, but the less averaged out those frequencies are. Higher time resolution, lower frequency resolution. Harkening back to leakage, if you were thinking that we can just increase the number of frequencies we test for by increasing our input size and having less chances of a frequency to not align because we just have more frequencies for them to align to, then here's the problem with that. We lose that special time resolution. You gotta decide what's more important to you at the time. If you really need to know the frequencies, then a higher frame size is better. But if you really need the timing for said frequencies, for example, beat or onset detection, then a smaller frame size is better. It's not a one-size-fits-all situation, but for our example, we're gonna go 1024 samples for our frame size, which also means that our hop size will be 512 samples long. And now that we have our window, hop size, and frame size, we can now start implementing a program using the basic STFT function in Nebrosa and Python to create a spectrogram. Actually, before we do that, if you see a different equation for the STFT on Wikipedia or wherever the case may be, don't be alarmed, it is the same equation. What they're doing is more or less shifting the window instead of just shifting whatever we're inputting, which is what this MH is doing for our input signal. This MH plus the N is more or less figuring out, okay, at what point should we start reading the audio, and we go to the frame size from that point. And so since M increases over and over again, it gives the new frames over and over again. I just wanted to clear that up before we continue, so don't be scared. It's the same equation if you see it on Wikipedia or not. All they're doing is just shifting the window instead of shifting just the start of the audio. But we get the same output anyway. Tomato, tomato equation. Same thing. Okay, we can continue. First off, we have a simple Python script that creates a spectrogram using Librosa. It's rather similar to the script made in this video, but instead of going through it in 30 minutes, I'm gonna go through it in 3. I hope you can keep up, and I hope I can too. We first load our audio into an array variable of floats for each sample, as well as load in the sample rate for our audio using the Librosa load function. For today, we're gonna use Formula by Aphex Twin to see if we get that infamous frequency monster once more. After loading in the audio, we then initialize the frame size and the hop size, which we are setting to be 1024 and 512 respectively. We then pass all our samples into this short time Fourier transform function from Librosa, along with sending in our frame size and hop size. The output variable STFT_Aphex is a matrix, or two-dimensional array, where each index of one axis corresponds to the frame size divided by 2 number of frequencies, and the other axis corresponds to the frame number. Because this is just a two-dimensional array, those axes are really just the indexes, with all the data inside the matrix being made up of complex numbers. We then convert these complex numbers into the power of each frequency by taking the absolute value of all of these complex numbers and then putting each of those magnitudes to the power of 2. We do this to get the power, whereas just getting the absolute values would give us the magnitude. I'm not gonna go into too much detail about the differences, but just know that the power would give us a better visualization of everything. We then call the make spectrogram function, which calls spectral from Librosa and plots everything using matplotlib. We can see that spectral takes in our two-dimensional array or matrix of frequency powers, the sample rate, the hop length, and defines an x-axis and a y-axis. If we were to run our program now, we don't really get a good representation of what we're looking for. But that's because everything is still linear. What we have to do is convert our matrix into a logarithmic scale, and also plot our frequencies logarithmically as well. It's more akin to how humans actually hear sound, and it's also how a good number of frequencies are plotted and shown anyway, but in doing so, we now get a full spectrogram of all the different frequencies. And if we were to zoom in on the right here, we also see our frequency monster friend, Richard D. James himself. Okay, cool. Is that 3 minutes? I hope so. Don't check. Please don't check. If you want to know how you can make this visualizer thing that I've been using throughout this video, then you can check out my Patreon. For that specifically, don't worry, it is for free. It's just, it'll make this video a bit too long than it actually needs to be, but it's also just a bit too scant to be its own video itself. This is just the best place for me to put it, so as long as you're a member, you can watch it entirely for free. That's it for this video. If you watched this entire video and don't know what on earth I was talking about, and you haven't watched my DFT video, then I think you know what to click on next.